To probe the unknown is the nature of modern biomedical research. And often along the way, we encounter the unexpected. But the unexpected can take a variety of forms, some of them less than welcome. This accident has been recreated to make a point. Working in a biomedical research lab is surely safer than the daily commute, but accidents do happen. The goal is to do the science, but at the same time, reduce the risk. What you might call practicing safe science. The laboratories of the Howard Hughes Medical Institute are to be found at institutions all over the country. Here at Cold Spring Harbor Laboratory, where biology has been pursued for nearly a century, is an apt place to draw some fresh conclusions about laboratory safety.
And it lines up precisely
with the pressures and competitive challenges of science today, do molecular biologists like David Beach still find time to be concerned about safety?
One of the main problems we have in the lab is actually knowing what the risks are. Covering yourself with phenol is a clear, simple risk, and the consequences are acute and dramatic. What we live with day by day is in many ways much more difficult. Is it more dangerous to dip your fingers into a gel box that contains ethylium bromide, or to mouth pipette some gamma-labeled P32, which nobody does? Which of those two is more dangerous? Or is it more dangerous to go and smoke a cigarette, or to get in your car and go home in the evening? I don't know which of those is the most dangerous. And that's in a way very frustrating. So the main problem I see is that we don't know what the real risks of each individual activity is. So we tend to act cautiously.
Although the risks of any given activity may be unknown, we clearly know the specific hazards. Or do we? How about looking at several everyday laboratory procedures and spotlighting them? In the first protocol, Arshad is preparing to equilibrate phenol. By the way, some questions, challenge questions, are going to pop up every now and then. Like this. Phenol poisoning can occur through which of these routes of exposure? Phenol is rapidly absorbed through the skin, and this route of exposure can cause poisoning as readily as inhalation. The fume hood, a great blessing, yet a source of distress for many a safety director. Here's one reason why. A vapor source placed in the hood lets us see what's actually happening. And if you take the trouble to pull the sash down to the marked level the way you're supposed to, yes, that's why you're supposed to pull the sash down. It does make a difference. Still, it's no guarantee. If something causes an air disturbance in the room, somebody walking past, or somebody closing the door on the way out to lunch, yes, even putting your own hands into the hood or taking them out can set up an eddy current. And of course, it doesn't require a red line to remind you that your work should be at least 4 to 6 inches inside the face of the cabinet.
One of my students was using radioactive iodide, and he was using it to iodinate a protein. So you tag a protein with a radioactive iodine. During this process, he obviously became contaminated. And tracing back now, what the problem was, how that arose, was found that hood was defective. So whereas we all thought that the radioactivity was being exhausted and diluted in the outside air. That was not occurring. I think this points to the importance when you're doing experiments that carry this kind of potential risk, to be sure that the equipment you're using is really functioning well. I think that's one of the lessons we certainly learned from that.
A search through the records of laboratory accidents came up with some eye-openers. Like this. Warm glass on a cold counter. A weakened seam at the base of the jar. A trickle of phenol. But phenol acts as a local anesthetic, delaying an awareness of the harm it's doing.
She first noticed it on her feet because she was wearing these open shoes, and it splashed onto the top of her feet, and she sort of started to yell as it began to burn into the top of her feet. What she hadn't realized, however, was that she'd actually poured it all down the front of her jeans, and it hadn't actually soaked through yet. After another 10 or 15 seconds, though, it began to soak through and contacted the skin of her legs, of her thighs. She developed quite severe burns that put her in the hospital for 3 or 4 days.
By far the worst I've seen were 2 accidents, and they both involved phenol. One was somebody trying to distill phenol, and the distillation apparatus blew up all over him, covering him with hot phenol. And the other was somebody doing a simple phenol chloroform extraction and having the lid pop off a tube and phenol distributed all over the person's arm. Both of those were very unpleasant.
Now in the lab, there's nothing quite like seeing an accident for yourself. I mean, this happened in full view of everybody in the lab. It was really a horrifying thing to see. And now, anytime anyone handles phenol in this quantity, the lab coat is the first thing they put on.
What should be the first action in response to a phenol spill or splash on the skin? Flush immediately in a sink or safety shower and remove the clothes there. And never use ethanol. It can enhance absorption and dispersion.
I don't think one should look upon safety or the kinds of things you learn to do in order to reduce risk as being onerous. It's really it's part and parcel of doing your experiments. You learn to do it to do things in a certain way and to keep the risks low. I had one bad experience as an undergraduate. I was a chemistry major, and I was carrying out what's called a Keldol reaction for measuring nitrogen content of a sample. And I did a very foolish thing. I poured concentrated acid into concentrated base solution that was hot. And what happened was absolutely predictable, but I wasn't thinking very clearly, and that is, it bubbled over right into my face.
The trick to having experiments work, particularly in molecular biology, at least in my experience, is concentration. Thinking exactly what you have to do, what you must do, and having it done the most effective way. And I think having to think about doing it in a safe way really helps one concentrate.
Preparing an agarose gel, Dory is working with materials that are not considered hazardous. But the microwave door was blown off its hinges and hurtled all the way across the room. Even when you make sure to loosen the cap on a bottle going into the microwave, the expansion of gases during heating can force the cap to set up tight. Better to plug the container loosely with Kim wipes. And how hazardous is ethidium bromide? Even though we know it's highly mutagenic, the hazards to humans are not well understood, and not likely to be, so it's prudent to avoid exposure. Which brings us to the question, which of these common ways of using ethidium bromide offer a significant exposure hazard? Handling the powder form in preparing a stock solution, and the high concentration in cesium chloride gradients make these two the highest risk. When your protocol specifies acrylamide for a gel, there are ways to reduce the hazards. Incidentally, what are the hazards with acrylamide? That's the next challenge question. Which of the following are hazards of acrylamide? If you said all those listed, you're right. In particular, as with any hazardous powder, measuring and mixing are the high-risk procedures. You use a spatula, don't you? Never shaking out the amount you need, which spreads powder around heedlessly, needlessly. And you work with acrylamide only in a hood, don't you? Because with any fine powder, even working carefully, some of it goes where you didn't intend. While the larger particles land nearby, the fine ones disperse throughout the area and stay suspended for an extended period as an aerosol. Wouldn't it be better to purchase acrylamide in solution or in pre-weighed quantities? Go the full route. Many of the chemicals used in the molecular biology lab can be obtained in a form that reduces the hazard. Even if it means changing a protocol, weigh the nuisance against the gain in your safety. Incidentally, that face mask you wear when working with substances like powdered acrylamide, it doesn't so much protect you from inhaling aerosols as keep you from rubbing that itchy nose with your contaminated gloves. Don't let a mask lull you into overconfidence. And speaking of face protection, what's a good rule of thumb for using glasses, goggles, face shield? Reach for glasses when there's a splash hazard with a small quantity of a hazardous chemical. Every year, people get splashed in the eye while just opening or closing a bottle or popping open a microfuge tube. Glasses don't do much good if they're in your pocket. Goggles are in order when handling a liquid that's highly caustic or in larger volume, say a liter or more. Choose a face shield when handling very large volumes of a hazardous chemical, or when there's a need to protect your face as well as your eyes. By the way, that includes any time you're removing a closed container from liquid nitrogen. And when working at a transilluminator, you always want the protection of a UV face shield. As Greg prepares for DNA sequencing, he's now ready for his radioisotope. Time for another challenge question. This one is about 3 common isotopes used in our labs. Match the isotope with its chief hazards. The eye and skin hazard is P32. Its beta particles can travel up to 20 feet in air. Inhalation and skin, iodine 125. It's the free form that presents the principal inhalation hazard. The beta particles of S35 can travel only about 1 foot in air, so the principal danger lies in hand-to-mouth contact leading to internal exposure. some of the things we use every day we tend to take for granted. If the centrifuge police raided your lab, what would they discover? Let's look into a few labs at random. And that's just the radioactivity. The levels of biological and other contaminants not so easily detected could be even worse. Bottom line, even though a centrifuge used for isotope work may have some level of non-removable radioactivity, it's imperative to remove surface contamination to avoid spreading it around. We never forget, but sometimes overlook, how a tiny bit of hazardous material can contaminate an entire work area.
$100 deposit for the Achieve sedan, MSRP $14,000.
System is working its way slowly towards us here on Long Island. Skies will become cloudy during the evening, some scattered showers developing too, but they'll end overnight, lows near 45. For Friday, partly to mostly sunny weather developing, high 60 to 65. It's going to be very cloudy.
Looks like an exaggeration. Truth is, it really happens.
It is almost an invariable correlation that the type of person who distributes radioactivity on the floor without telling anyone is almost invariably the same person who'll use the last bit of a reagent from a tube without telling anyone that it needs to be ordered again. That's a harmless activity, but it displays a lack of consideration for other people in the lab. And I think good lab practice, consideration for other people, and safety are three totally related issues.
When it comes time for Anne to do an electrophoresis, she knows the type of device used for sequencing operates at a dangerously high voltage. But how about the low voltage devices used with agarose gels? At 100 volts, what current level is sufficient to deliver a lethal shock? The answer is not very much. Even 25 milliamps can be life-threatening. So how do you keep your life from being threatened? A few tips. Be sure the power is off before you start making connections. Handle power leads one at a time, with one hand only, and never if your hands are wet or sweaty. Beware of loose connections that could allow sparks or an electrical arc. Keep the device away from a sink or wet area. When finished, be certain the power is off before removing the lid or reaching in. And if you feel a tingle when you touch the unit, stop using it immediately until it's repaired. Yes, of course, on some units it's possible to override the safety devices, in the process exposing yourself to grave unnecessary risk. And it's possible to continue using older or homemade devices without protective features. It's also possible to run an electrophoresis device unattended. But none of these are exactly what's meant by practicing safe science. The investigator had gone home for the evening, leaving his gel running. A modern device would have shut off before the buffer evaporated. The experimental work in progress of several investigators was destroyed. The lab was out of service for weeks. Now Anne is ready to take her gel down. Of course, she'll put on gloves before reaching into the bath. What's the most effective practice in using protective gloves? Surprisingly, the answer is B. The most effective practice is to change gloves frequently and when contaminated, because all gloves are permeable to some degree. All gloves are permeable. So whenever you're working with concentrated chemicals or large quantities, you should be wondering how much protection you're getting. For most purposes, the general use gloves are fine, but they have a very fast permeation time, which is why you should be discarding them and putting on fresh ones frequently, whenever they've been in contact with a chemical. When the hazard is greater, you want the greater protection of a glove that's specifically designated for what you're doing.
Safety is planning and organizing and controlling what you're doing, not responding in a rush, not hastily doing something, not thinking about what you're doing. Leads to unsafe things, right? And the best science, the best experiments, the best experimentalists are people who plan everything. They have complete control of their experiment. They know every reagent and how it works. They have it all organized before them. They have a protocol sheet they're going to do, and they're going to follow that protocol sheet, and they systematically work through. And when they put all that protocol and this experimental design together, they incorporate the fundamental good rules of safety. That's the best experimentalist. If you can design your experiments that way, you will be safe.
In a lab where the work involves handling human blood or tissues, the safety issues take on a different complexion, which means you should be thinking about questions like this. What is the risk of hepatitis B virus infection for lab workers relative to the general population? Two to 7 times as high. But the good news is that you can essentially eliminate the risk by being vaccinated and using good laboratory practices. And speaking of good lab practices, if your work involves handling human blood or tissues, grade yourself on whether you are 100% consistent about doing each of these important safety steps. Making sure all glassware and other disposables are appropriately decontaminated before washing. Disposing of all contaminated materials according to the regulations of your host institution. Keeping your wits about you when disposing of sharps so they don't end up someplace where they'll be a hazard for the housekeeping staff. Washing your hands thoroughly when finished, even though you've been wearing gloves. Conventional wisdom says we tend to grow careless about routine things, like wearing the lab coat and avoiding shorts or open-toed shoes, while using all due caution about the major hazards. So this should be easy. Which laboratory accidents involving blood-borne pathogens can cause infection? Inoculation and a splash onto mucous membranes or broken skin are the primary laboratory hazards. Infection by aerosols is unlikely. But of course, there's more to lab safety than just knowing the hazards.
Anyone who screws up with TB threatens the life of everybody else in the lab. And everyone knows that, so that the need for consideration is the most serious and important thing we have to worry about. Much less concerned, for example, that if someone spills bugs or has an accident, we can deal with that. We know how to deal with that. Most concern is that if there is an accident and someone is afraid to report that, feels that they'll be punished or severely criticized, then that completely decimates the whole cooperative spirit of the lab and puts everybody at risk. So the challenge has been to have everybody participate.
Our final category, the kinds of accidents that are not related to a specific protocol. Many accidents happen away from the workbench, especially when you're transporting something. But if the containers are sealed or are in secondary containers, it's not a big problem to drop, bump, or bounce them. Accidents happen when what you're doing is so routine or familiar you take it for granted. When you're thinking about other things, distracted, not focused. When you're in a hurry, under stress, or just not paying attention. Those are the times you should be shifting into high caution. Thinking about where the risks are. Making your actions deliberate. Accidents happen when you're doing some dull task that doesn't require any brain power. Accidents happen when you're doing everything by the book and something stupid takes you by surprise. And they happen when you're excessively fatigued.
When you're too exhausted, you're not thinking about what you're doing, so you're very likely to mix the tubes. You're very likely not to follow the protocol. So it is also bad for an experiment to do things in a hasty way or an exhausted way. It doesn't work because you're not alert.
I regard safety as intimately related to good laboratory practice and simple consideration for other people in the lab.
There is nothing inconsistent between a well-done experiment and a safe experiment. And in fact, they almost have to go hand in hand, because if you don't have the control to do a safe experiment, you're not doing the experiment right.
No reason, whatever, why you can't do good science safely.